and two more for Australia with different labels. And here you can see the result of the classification on those networks. Here that the data signals was actually registered by the sensors, shows that BLSTM and ULSTM actually GRU, the length of signal is effective on the classification, but the length wouldn't be effective for those that are it's kind of convolutional networks. And mixing Z-score scaling with STFT increase the classification accuracy. And in 35 Australian dataset, the accuracy of classification was 1 or 100% with GRU, CULSTM, and CBLSTM. But data was not consistent in 35 Australia. That's the conclusion from the first part. Simpler networks, the length of signal was effective on the simpler signals, simpler networks, but it wasn't effective for the more complicated ones. And in the next section, the classification model is a mixture of all the network, all the signals, and the network is responsible for detecting and quantifying the analyte concentration, which I mean is that considering the first data set, it was labeled, as you can see here. Actually, the class 1 was those signals or segments that there wasn't any analyte in the signal on the sample. Label 2 shows the adenosine with 1 nanomolar concentration, and it continues. Here, the Australian data set, both segments shows that they are 1 nanomolar, and the analyte is Australia. And here I also added the broken transistor. And so there was 12 classes, and the network is able to also, shows the anomalies for broken transistors, broken sensors. The networks was those that I showed before, those 7 networks, and this graph is the performance metric, actually the accuracy of the networks. I forget to space this here. The conclusion, I think. The result was the same as the previous one, classification method. And the conclusion, the contribution, I think, might be automating detection and quantification and applying cost-effective method.
So you did a quick job to improve the load factor in terms of the data augmentation. in terms of the data, yeah, back population. So I think it's effective. And I'm thinking if for the group center, so your algorithm can repair the data. If, for example, suppose that I have some longitudinal center data, if some segment is abnormal, then we can repair the data, right?
Actually, we should use those another often for the network stuff. Broken transistors doesn't show anything. No, there was kind of signal, for example, here in this part, this jump shows that the sensor is working and just, it's working and registering change of constant concentration of samples. But here, the data cannot be trusted because, we can prepare these parts by autoencoders after training, and it might increase the accuracy or performance of networks, but here I don't think that works.
I agree for the new data augmentation method that is more effective than the first paper. It was some basic, very simple data augmentation. So the new one you propose, I think it is more effective. But it's not affected by it's not required to be all the signal segment is the same length. Now there's no such requirement. It can be flat, more flat. Yeah, I think it's okay. Yes. Very nice. So which journal are you going to target?
We should start with signal processing.
The part is made good.
My main concern is that the processing time or reviewing time is very long.
Yes. And is it? And you already have told you.
Okay. It's fine.
Thank you. Very nice. Anytime. Ready?
You have Zoom,
Oh, it's actually
go into Zoom,
Yeah.
and then screen share it. Do you use Zoom?
That's what I like.
It's screen sharing one.
No, you can present. Anything? Hello.
Oh, there it is.
Thank you. All right, my screen is blank. I can't see anything. No, it's not working. Like I was supposed to have notes and everything, but it's not working there.
And it doesn't matter. You can see the other thing on your side. The other thing.
It should be okay.
Oh, yeah, but I can't see my notes.
Oops.
Okay. See that actually works. Yep. So hi everyone, my name is Annika. I'm a second year student, so you guys are all much older than me. But so I'm doing a BSc in measuring physics and imaging technologies, and so I'm going to do a presentation on this research paper, the optimal design of array coils for multi-target adjustable electromagnetic brain stimulation system. And so basically I'm just going to be comparing this system with some of the traditional models and just the methods. The outline of this presentation is looking at the traditional models, like the methods and limitations, and then looking at the model that is in this research, which is the multi-brain area close stimulation, and their methods and limitations, and then doing a comparison of both methods. So starting with traditional methods, we have invasive models and non-invasive models. So invasive models are very precise and they target specific brain regions and have good focus and have fast response. However, it requires like surgical implants and stuff. So starting with the first model, we have deep brain stimulation, so that's DBS, and this involves the implantation of electrodes, which you can see in the image over here. And so this model, so the electrode then modulates the neuroactivity in the brain, and this model was successful in treating diseases like Parkinson's disease, essential tremor, and dystonia. Another invasive model is this optogenetics, and this model basically controls neuroactivity through light-sensitive proteins. However, because this model requires the genetic modification of neurons rather than the foundation of electrodes, it's because of the complexity is more commonly used on animal research. So going to non-invasive models, we have the transcranial magnetic stimulation, so TMS. This model uses pulse magnetic fields to induce electrical currents in the brain, and then that affects the neuroactivity.